Hello and welcome once again for another ES340 video. This is ES340 Day 19, Part A, the Clapeyron equation. So during, we'll start off by doing changes in phase and work our way, out to pure phase, or when there is no change in phase. So starting with the changes in phase, we may as well just talk about something that we've been talking about a lot in the course, which is when you change in phase from liquid to vapor or vice versa. Okay, so the change in phase there. There are other types of changes in phase, of course. Obviously going from solid to liquid, or you can have solid all the way to vapor. You can have all these different types of changes in phase, but we'll focus on the cases that we've been dealing with thus far. So hopefully at this point you kind of have an idea that the TDS equations are important. And this is just going to further emphasize that. If I integrate this, what I find, going, in this case, going across a phase change from liquid to vapor, or vice versa, let's say F and G will be liquid and vapor, as is denoted in your book. Then what I find is Hg minus Hf is going to be equal to T times Sg minus Sf. Or Sg minus Sf is equal to Hg minus Hf over T. Now just remember that this is the enthalpy and entropy specifics in each case, but this is the specific enthalpy and the specific entropy. Okay, so now going directly now, I hope it becomes kind of clear here that we can get useful things just going directly from these differential equations that are given. In differential form, we can start deriving a bunch of useful relationships that allow us to give very accurate predictions of things that are going to happen in thermodynamic variables. And this is the whole point of this section of the book. Okay, so furthermore, what we can do is recall that in the previous section we discussed a bunch of different relations that are called the Maxwell relations, and one of them was that we have ds dv holding t constant is equal to dp dt holding v constant. Now for the phase change, there we go. For the phase change, from liquid to vapor or vice versa, what we have is, you should recall that we already knew this to be true, that the temperature stays constant, right? The temperature and the pressure stay constant. So what we're going to say is, during a phase change, dp dt is equal to, holding the specific volume constant here, is it going to be equal to dp dt at the saturation value here, because these things are held constant during the phase change. Okay, so this obviously, starting from a phase change simplifies things greatly because of these things. We'll see in a moment when you don't have phase change, but this simplifies our process here. So using this fact, then what we can do is we can say that Sg minus Sf is equal to dp dt sat times Vg minus Vf. Okay, and what happened here was that we did an integration. Maybe we should actually do the integration so that you can see this. And I forgot one piece here that that we need, which will make this much easier to see. So then, this relationship then implies that, using our Maxwell equation up here, it implies that ds dv holding t constant must be equal to, well, we just said that this equation can be related to this, so it becomes dp dt sat. Okay, and to show this implies this, but obviously I should probably actually perform the integral, right? So it just ds is equal to, the integral of ds is equal to dp dt sat. Remember, this actually can be, this is held constant here because of the fact that we're dealing with a excuse me, the fact that we are dealing with a phase change, dv. And hopefully now you can just see that if I go from F to G, then this formulation pops right out, right? Okay, so this is close to what we're looking for, and basically the last step here, going from this equation down here, is that we get dp dt at saturation is equal to hg minus hf over t of vg minus vf. The only thing that you have to note is that we used the equation up here. Let's call this 1. Let's call this 2. And I'll let you do that part because that's simple enough. But if I combine 1 and 2 and I rearrange, this is the equation that I get, and this is the Clapeyron equation. So this is actually something that, and it's obviously related to the phase change, but this is something that can actually be used to check consistency in data, to make sure, because the behavior should be something like this. Now, what if it is a different type of phase change? Well, then we just get dp dt sat is equal to h double prime minus h prime over t times v double prime minus v prime, where these represent the different phases. So we've actually now kind of generalized, if we do this, we actually have generalized even beyond what we typically have dealt with inside of the course. Okay, so inside of the course, we've mostly dealt with phase change, or we've only really dealt with phase changes between liquid and gas, but obviously there are different types of phase changes that can happen that involve solids as well, and we've just kind of skipped entirely over that. But this equation stays valid even in those cases. So you can actually kind of generalize out beyond what we've dealt with mostly in the course at this point. So you can kind of see that this in a lot of ways, this chapter kind of binds everything that we've done together, and even allows us to expand beyond what we've mostly dealt with in the course. So I think of this chapter as being sort of a glue chapter that glues everything together, although it's a bit more mathy. In any case, you can actually note that going back to the VG and VF case, VG is typically much, much bigger than VF. This is something that physicists generally like to do. We like to make these kinds of notice these kinds of things. So that means that VG minus VF is approximately equal to VG. So if that's the case, then basically we can replace VG, right? Also assuming that it's ideal gas. So if we make two assumptions that VG is much bigger than VF and that the pressure is an ideal gas, then we can low enough that it behaves like an ideal gas, then we actually can simplify this equation, and we can say dp dt sat is equal to hg minus hf over RT squared over P. Right, so we just substituted in RT over P for VG into this equation here. And if you do that, then what you end up getting is RT squared, obviously, over P. Now, because of the rules of derivatives, we can actually move this p over, and it becomes. I know it's weird to write it this way, but this is actually something that that does sometimes get written. So basically, we move the p inside of the derivative term there. And so what we're left with is our hg minus hf over RT squared. In this scenario, right? Assuming that it's an ideal gas and that the specific volume is very large relative to the liquid value. So this actually becomes the Clausius Clapeyron equation. Okay, so that's obviously just dealing with a couple of assumptions that it's an ideal gas and that there's a big difference in the vapor specific volume relative to the liquid specific volume. Okay. But all of this was the Clapeyron equation relative to a situation where we have a change in phase. So the next question would be, what if there is no change in phase? Well, this leads us into equation. This should look kind of like a familiar form here now. This leads us to what if we have no phase change? Well, we can actually start from an equation that looks like this. Now notice what this implies, of course. This implies that we have some function s of tv, right? Now we have a function of two variables, which obviously makes things like taking the integral more complicated and stuff. So before, with the phase change, we had some simplifications that had happened because of the fact that pressure and temperature are constant during that time. In this case now, we have multivariable. This is why this case is a little bit more complicated. But in any case, we can go back again using the Maxwell relation, one of them. There are many Maxwell relations, but we can use one of them, which again is that ds dv held at constant t is equal to dp dt held at constant v. So that means that my equation becomes this. It becomes ds dt held with v held constant plus dp dt with v held constant dv, using this Maxwell relation. Let's call this 3. So I substituted 3 in there. Okay, and we can continue going further down the line. We can also do things in terms of the specific internal energy. So du, well, that's going to be equal to du dt of v dt plus du dv of t holding t constant dv. Okay, and this formulation should be very familiar now, because this is exactly why we were discussing exact differentials, right? So this is going to be a common theme. You see the S in terms of the entropy in terms of T and V, U in terms of T and V, right? So we can, this is exactly where we were talking about that simple compressible state that we can use, where we make the assumption that everything depends only on two variables. However, remember that we did have something that looked like this, du dt, and that was, if I hold the volume constant, that was my CV, which obviously is of course a function of t. It doesn't have to be constant, but if it is held constant, then obviously you already know the variety of different equations that we came up with relating this. So this actually maps, again, directly back to our equations that we had before, and hopefully now you can start to make sense of what's going on here. Basically, the equations that we found, oh, this is dv, not du, that we found throughout the course can be directly mapped back to these differentials, right? So we have equations that start off as differentials, and the relationship between P, pressure and volume and temperature, can all be mapped back directly to this set of equations that we have before us. Now, if we can I'm not going to go through all the steps here, because I think that it's not really completely necessary to see every detail about everything. You can go back through the book if you like and work through some of these equations. Excuse me, but we can find equations such as this, ds dt, holding v constant, ends up being equal to cv over t, which you already kind of know, that this relationship, if dv is equal to 0 and dt is not. So you've seen a relationship sort of similar to this. Similarly, if dt is equal to 0 and dv is not, then we can get an equation that looks something like this. Okay, and like I said, I will let you work through those kinds of equations. If you wish to actually go through the derivations, we'll do some examples that relate back to this section, so that you can, map them back nicely. But these are equations that we can come up with directly from directly from the differential versions of these equations, right? The du is equal to this, ds is equal to this. And starting from this now, we can actually derive something that we saw before, oops. So using this and this, which comes from this equation, this part, T, and the Maxwell equations. Okay, so you can actually use the Maxwell equations and things to derive these kinds of things. Then we can get the difference in entropy, for instance. Now this comes directly from these equations, the differential form. We can also get them into the integral form, this is going to be a key kind of thing that you'll find when you are doing things like heat transfer, or when you're doing fluid dynamics, these kinds of, or fluid mechanics, these kinds of classes. You'll start to see that the differential form and the integral forms will be important in solving out for various things, right? So this is it's the same kind of idea here. We're just getting to it sort of towards the end of the class. But this equation should look pretty familiar at this point. The change in entropy. And we can get a similar equation for the change in internal energy, right? So this was the change in entropy up here, change in internal energy. You can see that in a variety of cases these may be explicit in different types of variables. Remember that term explicit, which I at least covered in I might not have covered it in previous videos, but I at least covered in class during the clicker questions. Okay, and then you can get very similar. Again, you can go down through. I'm not going to derive everything, but we can also remember that Cp is equal to dH dt holding P constant. Okay, so when we hold P as a constant variable, then we can get a bunch of equations, something that looks like, for instance, dH dP holding T constant plus T dV dt holding P constant minus V dP, and setting that equal to this, T ds dt P minus Cp all times dt. And this can be derived. Your book goes through the derivation. And under certain assumptions there, like dP is equal to 0, but dt is not, we get ds, very similar to the set of equations above. Excuse me, except now this is not related to the internal energy, but it's related to the enthalpy. And then, of course, assuming dt is equal to 0, but dp is not. Okay, and in all of these cases, we can, under these various different assumptions, we can actually get back our equations, right? So S2 minus S1 in this case is equal to the integral from 1 to 2 of Cp over T dt. We actually can get back to the equations that we were dealing with earlier in the course, or something that looks very similar to those equations. And under obviously certain assumptions, then these equations become the exact equations that you saw before. But I will note that, of course, in this case, v minus t dv dt p times dp. Of course, all of these different equations under different types of assumptions you have seen at some point throughout the course, except for the parts that we get through to do the derivations and the Maxwell equations. That part was not here. But like these integral forms, you've seen something that at least looks very similar to them earlier in the course, and it comes directly from this manipulation that we're doing here. So we have the Maxwell equations that we can use, and the variety of different now ways of manipulating and integrating these different things, and all of that leads back to exactly what we've been doing throughout the course, right? We're very often interested in the change in enthalpy, or in the change in entropy, or in the change in internal energy, right? Because these all map back to pieces of the different equations that we were dealing with: the energy balance equation, the energy rate balance equation, the entropy balance equation, the entropy rate balance equation, the exergy equations, right? So all of those can be directly mapped back to doing these kinds of manipulations. So we think of them as being a multivariate functions, right? Functions of two variables. Temperature can be thought of as a function of volume and pressure. Pressure can be thought of as a function of temperature and volume. Volume can be I don't know if I said that already, but you get the idea. We can think of these as as functions of, each of them can be thought of as functions of two variables. So this is hence the need for the partial differential equations, but also under the variety of different circumstances and these manipulations with the Maxwell relations, we can get back all of the stuff that we've done in this course. So this sort of, as I mentioned before, glues the course back together. Okay, so that's all that I have for this video. There'll be a second part that I'll see you again soon for.